But then I was wondering that maybe I could buy it. I was like, yeah, on the last one.
I remember the same thing he did. He worked. And he learned something like I think we have this. I'm like, I don't have that.
I have. And then basically, do I get home? I bought one and it got me one and it now it's also so
We had to drop one.
there it is. There, whatever. And I think I had it between like my mind or whatever, and then so like, oh, I probably could use this.
Yes. Today we're going to finish chapter 8. Yep.
And also I don't think it would come out.
All right. So on Wednesday, we got as far as ionic radius. Your next mastering's not due till Monday night. Your exam is on Wednesday. We're going to do a group quiz today. No quiz Monday. Instead, we're just going to spend the time reviewing, which should be like a quiz in theory, but no official quiz. What was that? I'll think about it. Maybe if you get 100 on your test, I'll consider the quiz 100. I think that seems fair. Okay, fair is probably not the right word. Let's see what else. Oh, the practice test is online on my personal website. So if you want to kind of over the weekend try the practice test, it's like 25 questions, some multiple choice, some short answer. You can go ahead and work through it and see where you get stuck. And then when you come in on Monday to class, we can work through wherever you were confused on. And if you weren't confused at all, then maybe somebody in here can confuse you and then we'll solve it. Seems like an option. All right. So last time we did cations, which are elements that have lost an electron, and we saw that the Z effective increased, so their radius decreased. So that means we have to do the other version where we have an anion. All right, let's pick an anion that doesn't have a million electrons. We'll try chlorine. All right, so let's say I have chlorine. How many electrons should chlorine have if it's number 17? 17 electrons, all right. So what should the first orbital be called? 1s2. Okay, then what? 2s2. 2p6. 3s2, and then, yep, 3p5. We'll do both the orbital diagram, just like we did this one. We'll do both orbital diagrams, so we'll do the Z effective. All right, if I want to make the anion of chlorine, what charge should I give it? -1, right? I tell it that it's -1 because it's gained an electron. So what's the only orbital that's going to change? The very last one. So 1s2, 2s2, 2p6, 3s2, 3p6. All right, so now let's calculate our Z effectives. All right, so we started off with total number of electrons. What's the total number of electrons? Oh, sorry, total number of protons. Total number of protons for chlorine regular. 17. All right, which value of N are the valence electrons? The 1s, the 2s, or the 3s? 3s, right? So these are the valence. So how many valence electrons do I have? 7. So how many core electrons do I have? 10. Or you could just count up the core electrons. That'd be fine too. All right, so what would be the Z effective for this? 7. All right, so then, let's see. Did I do that right? Core electrons. Yep. So again, total number of protons, 17. Now this is where it gets a little different, right? Because now everybody's full. So the number of valence electrons is 0, sort of. This is where it's not a great argument, in that these guys are technically all in the largest shell, but they're not going to act like regular valence electrons. They're going to look like a noble gas, right? So if it's acting like a noble gas, is it going to be reactive? Not in its current state. And so it's going to look like, it's going to look slightly different. So now these are kind of considered let's see what's the best way to phrase that. Not exactly valence anymore. Not exactly valence. And so now all of these would be in the core. Does that make sense? Sort of. All of these would be in the core. Mm-hmm. Question.
Then why didn't we go with calcium?
Calcium. Because it has the 4 energy level available to it, and so it could have added on into the 4s, but because we reduced an energy level.
So anions, if you reduce, then it's full.
Yes. Yeah. So Z effective is not a great argument. It kind of helps us see what's going on, right? Because the Z effective went from 7 to 0, which is a decrease, which then tells us the radius should increase.
Which makes sense if it gains
Right.
an electron, the positive charge.
Yes. Yep. So it kind of helps explain what we already see. So,
Radius.
yep. So the Z effective has decreased, so we would expect the radius to increase, which is what we see. So this half are all the cations. This figure's in your book. And this has all the anions. And so you can see the one we did for calcium. Where's calcium? Calcium was this big, and now its ion is that big. And if we look at chlorine, its regular atom is this size, but when it gets an extra electron, it's now this size. Right? So if I lose an electron, my radius decreases. When I gain an electron, my radius increases. Which kind of makes sense in a few different ways, like the Z effective, or I just have more electrons in my radius, right? So I went from neutral to -1, so I'm going to push out farther. I went from 0 to +2, so it's going to shrink in because there's just less electrons. So there's a few different ways you can kind of think about what's going on there. All right, so now we're going to talk about the last, I think it's three periodic trends that are all interrelated. So ionization energy is the energy required to remove an electron from an atom When we look at ionization energies, the energy is a positive value, as that indicates that energy is absorbed to release an electron.
Is that OS?
Where are you looking?
Right after value.
Oh, AS.
When it says from a gaseous atom, does that mean it has to be a non-metal?
No, it just means that whatever element I'm looking at has to be in its gas phase so that it's not interacting with somebody else.
Is there some elements that cannot be in that though?
You can force any element to be a gas. Just may require a lot more work. So, release. Sorry. The energy in a, I'll write cleaner. The energy in a positive value, is a positive value, as that indicates that energy is absorbed to release an electron. So again, this figure's in your book. It looks a little funny on my slide. Let's see if I can zoom in a little bit. All right, so here I have just a little bit of the periodic table where we're looking at ionization energies. And you can see that the ionization energy of lithium is 520, where the ionization energy of fluorine is 1681. So, which of these two, 520 or 681, is the lower value? All right, 520. If it's a lower value, what does that tell you about the likelihood it will release an electron? More likely, right? Takes very little energy, so it's more likely to release an electron. So lower energy means more likely to release an electron. What do we know about this, the alkali metals and the alkali elements in terms of their likelihood of releasing an electron? Very high, not very high. Are they likely to become a cation or not likely? Right, they are likely. Like, that's the one thing we talk about all the time, right? Lithium, sodium, potassium, those guys want to release an electron. It gets you to a more stable electron configuration. So these two columns, columns 1 and 2, form cations, as their energy is very low to remove that last electron. If I am looking at the halogens, fluorine, chlorine, bromine, iodine, and they have a much greater energy requirement, what does that tell you about the likelihood that they are going to lose an electron? Seemingly unlikely, right? Not likely.
7A.
Yeah, 7A.
So from that, could you say that alkali metals are more reactive?
That's such a broad statement. I would, in some ways, yes. Yeah. Depends on what the reaction is, but yeah, they're going to be, in terms of ionization energy, they are more reactive. What about, what's this column called over here? Column, very last, 8A. Noble gases. Why is their energy so much taller than everybody else? They're complete, right? They don't want to lose an electron. They just got all the ones they needed. So their energy is even higher than a halogen. A halogen is more likely to become a +1 than a halogen, or than a noble gas. All right, so our trend is going left to right, going this way. That is increasing ionization energy. And then going this way, going top to bottom, that is decreasing ionization energy. So why would, pick a random element, but look at the halogens. So why would iodine be less energy to remove an electron compared to fluorine? A lot has to do with how close it is to the nucleus, right? So iodine has 53 electrons, and that number 53 electron is in the n equals 5 energy level, which is pretty far away. And so relatively, as long as you're looking up and down the same column, it's going to be easier to remove that 53rd electron than it would be to remove electron number 9. Right? Again, that kind of makes sense with what we know. With Z effective, all kind of comes together. Everybody looks super pumped by this. Okay, good. You guys looked equally excited on Wednesday. It's probably just so much information. All right, in that case, let's talk about a related topic called electron affinity. Electron affinity is a measure of how easily an atom will accept an electron. So what kind of molecule would I call an element that has gained an electron? Could be halogens, a more generic name for everybody that gains an electron. Anions. These are just in general anions, right? So it's a measure of how easily I can make an anion, basically. And the previous one was how easily, right, electron, or ionization energy is a measure of how easy can I make a cation, right? Similar in terms of what kind of chemistry is going on. All right, so if it was positive energy for my ionization energy, that indicates energy is being absorbed to release an electron, what sign should electron affinity have if I am adding an electron? Negative values, which is what we see. So electron affinity always has negative energy values, as that indicates energy is released when an electron is absorbed. All right, so negative numbers are always weird to think about. The bigger the negative number, right, the larger the negative number, the more energy is being released, so the more likely it is to take on an electron. Go ahead and write that down. Let's see, I'll write it over here. So the greater the energy, negative energy value, the more likely that element is to gain an electron. So, looking at our table of electron affinities, what family of elements has the greatest negative energy values? Right, the halogens, these guys. What do we know about their likelihood to take on an electron? Very likely, not likely. Extremely likely, right? So again, it makes sense with what we know. This is the greatest electron affinity values, which are the halogens, and the halogens are very likely to take on one more electron. So they have the greatest electron affinity. What family of elements is the absolute last choice to take on an extra electron? I'd say it's a toss-up, but I would choose this column. What are those guys called? Noble gases. What's the likelihood they're going to take on an extra electron? 0, which is what it says, 0. Right? Not likely. Okay, second place, least likely. Yeah, probably in between these two. Right, lithium would consider it. Same thing with sodium, because it's, if I was lithium, right, I'm at 2s1. There's some arguments to be made that 2s2 would be a better not better option, an option, right, fill up the 2s orbital. But if I look over here at beryllium, it already has 2s2. It has 1s2, 2s2. If I added another electron to it, it would have to make a new orbital available. And then becomes unstable.
So those are the least likely, not the A1.
2. Yeah, 2 would be my second choice least likely. Just because they are at a fairly stable organization, right? Because everybody in here has their s orbital full. And so they probably wouldn't want any more.
From that logic, would
Yeah.
D, if like D10 would also be less likely?
Yep, it would be on the low end also. You can tell, transition metals are weird. That's why they're never included in any of these tables.
No one likes them.
They have, it's because, I'll tell you in a secret, this isn't exactly true. This is a hand-wavy explanation of what we know to be true with some values that kind of prove it. But I'm giving you like electron affinity for kindergartners. We're not ready yet. You don't have enough chemistry background to really talk about it because there's all those great transition metals that when you get there, you're like, oh, those were all lies. Yes, I'm lying to you. This is not exactly how it works. But it's pretty close, and you in Gen will get the right idea. And so the more chemistry you take, the more you realize I lied to you in Gen Chem. But it's for your own good. It's for your own good. You're just not ready yet. It's like how you explain things to a toddler versus a teenager. A toddler's not ready to hear it because they don't have enough knowledge. So, D metals, weird cats. So, because they can actually go both ways. They're like the swingers of the periodic table. They can be anions or cations. They can be somewhere in the middle. It's weird. They're weird things. And so these rules don't apply. So, off track, as usual. That's my thing.
So does this one have like an exact, like larger, increasing?
Oh, yeah, it does. So we're going to do electron affinity. We're going to going this way, so left to right. We see increasing electron affinity with a limit. Obviously, these guys don't count. That is confusing. No, this has the greatest affinity because it's most likely to want an electron. For ionization energy, if I increase the ionization energy, it's not likely to lose one. Yeah. I mean, if you just keep thinking, okay, if I'm going lithium to fluorine, fluorine will always make a negative, which means it has high electron affinity. Lithium wants to give it away, so that's low ionization. They're all interrelated. They're all telling you the same information. And then which way am I going on this? Let's do the cross row. And then... Yeah, I was trying to draw the arrow where everybody can see it. I mean, in general, going up, you see increasing electron affinity. Increasing, yep. Right, because fluorine's the biggest, so that has to be at the top. All right, so then the third property we're going to look at with periodic trends, which is our last one, is related to electron affinity. They're very similar. The difference is we need electronegativity to talk about things being bonded together. So both ionization energy, electron affinity, and radii are all about an atom by itself in free space not interacting with someone else. Electronegativity is a measure of an element bonded to another element. How likely is it to pull the electrons from the bond to itself? And we'll use this in chapter 9 when we get to it, because we're going to start doing Lewis dot structures. Oh, back into like some realms of confidence, hopefully, Lewis dot structures. And then I'll kill you with not knowing what we're doing after that with some Vesper theory. And then we'll swing back up with gas laws. So, a little PV equals nRT action. So, a little up and down. So, all right, so electronegativity is very, very related to electron affinity. So, electronegativity electronegativity is on a scale of 0 to 4, where 0 indicates that it won't attract electrons at all, and 4 means strongly attracts electrons. All right, so knowing what we know about electron affinity, what element is most likely to have a 4 on the electronegativity scale? Fluorine. Fluorine was our highest ranking electron affinity. Well, fluorine. It's going to be one of the halogens for sure, right? And I know you can't see this figure. I'll try and zoom in a little bit. Oh, that's not bad. Fluorine is actually the element that has a 4.0 electronegativity. So it is the most likely to pull an electron to itself. And it's really because fluorine only has 9 electrons, right? So putting in that 10th electron, that energy level is really close to the nucleus, and so it really has a strong pull still on all those electrons. What column should have the least electronegativity, the least likely to pull an electron to itself? Noble gases. In fact, they're not even on here. That's how unlikely they are. Noble gases are going to be zeros. All right, so noble gases are unlikely. They're at the 0 end. All right, and then this guy down here, FR, francium, is around 0.7 on the scale-ish. It has a very low ability to attract electrons to itself. So, knowing that fluorine is the highest and francium is the lowest, which direction does it look like an electronegativity increases? Does it increase left to right or right to left? Okay. So it's going to increase going this way, so left to right. And then what about if I look at a single column? Let's look at the halogens, right? Fluorine compared to iodine. Iodine has a 2.5 electronegativity. So is it decreasing down the column or increasing? Increasing up the column or decreasing down the column, both would be true. So electronegativity decreases going top to bottom, which again makes sense, right? Because if you are iodine with 53 electrons, there's not a lot to gain by getting that 54th electron. You're in energy level, what is that, 5, and so there's not a strong desire to get an extra electron in there. So fluorine's always going to be the highest. Noble gases are zeros, and then column 1A is going to be your lowest. All right, how about that for trends? Pretty exciting. Yeah, you can save the applause for after the class. That's fine. I'm already standing up for the standing ovation. I'll wait till later. At this point, unless there's questions, any questions about Chapter 8? In that case, why don't you find your groups? We'll go ahead and do the group quiz.
We need a calculator.
Let me check. No calculator.